So example 9.1.1, hypothesis test for two population proportions. So do husbands cheat on their wives more than wives cheat on their husbands? So suppose you take a group of 1,000 randomly selected husbands and find that 231 had cheated on their wives. So right here, this first number, that is a sample size for our group 1. And we are categorizing each husband as a cheater or not, so we've got qualitative data. So this 231 is a count, so that is our X sub 1. And then suppose in a group of 1,200 randomly selected wives, so here's our second sample size, that 176 had cheated on their husbands. So again, for qualitative data, we have a count in a category, so that is a value of X, and the subscript 2 for the second group. So do the data show that the proportion of wives who cheat on, the proportion of husbands who cheat on their wives is more than the proportion of wives who cheat on their husbands? And it says to test at the 5% level. So that gives us our level significance alpha is 0.05. All right, so again, we're doing a hypothesis test, so we're going to follow through the steps from Phantoms. And again, we decided as we read through this that we have qualitative data. And so that means our parameter is going to be p, and from that we get information out of the random variable p hat. And so again, these wordings exactly like what we had in the last chapter, except now it's just, double duty because we've got two groups now for that. All right, so we are going to let p1, just because the first group that they gave, it does not matter how you number your groups, but I just use the first group that they gave me data for, I call group 1. So in this case, p1 is going to be the proportion of all husbands who cheat, and P2 is going to be the proportion of all wives who cheat. And then we're going to get information about those parameters from our sample. So our random variable p hat 1, this is going to be the proportion of 1,000 randomly selected husbands who cheat, because that was our sample size for that group. And then the group 2, this is going to be so p hat 2 is going to be the proportion of 1,200 randomly selected wives who cheat. All right, so our second step is to set up the hypothesis. So the null hypothesis H sub 0 and the alternative H sub A. Now in this case we have two parameters, P1 and P2, and the null hypothesis is going to say that those are equal. And in this case, our group 1, this was the men data, and group 2 was the, or actually, use the terminology here, the problem. These were the husbands. And group 2 were the wives, and so in here we want to know if the data show that the proportion of husbands who cheat is more than the proportion of wives who cheat. So we want proportion of husbands to be more than proportion of wives who cheat. And then they gave us the value of alpha that we're supposed to use is 0.05. So now let's see, I'm going to move that over here so that I can write something else over here. All right, so when we have two groups, there are two different ways that we can write this statement, and we need to be comfortable with both, because how I've currently written it is going to be the way that will be easiest to interpret it when we state our conclusion in context. But when we actually go to draw the distribution, so we can see where to center that, if we just subtract P2 from each side here, we're going to get P1 minus P2 equals 0, and P1 minus P2 is greater than 0. Okay, so both of these sets of statements mean exactly the same thing. All right, so our third step is to check the assumptions for the test. So for all of these tests, our first assumption is that we've taken a simple random sample. For this particular class, we're just going to basically assume that's been done. So a simple random sample of 1,000 responses about cheating from husbands is taken. That was stated. And a simple random sample of 1,200 responses about cheating from wives was also taken, and that was also stated. All right, so the second condition here is that we need to have independent samples. And so in this case, The samples are independent since each group was randomly selected. We probably don't have any like husband and wife pairs in our data. And then for qualitative data, for the current test that we're looking at, it's important that each object can go into only one of two categories. We're going to get a different test later if there are more than two categories. So in this case, each person in the study either cheated or they didn't. And then our next condition, we need the counts in all the categories, so both categories for both groups. We need all those numbers to be at least 10. So we need x1 to be at least 10. We need n1 minus x1 to be at least 10. We need x sub 2 to be at least 10. And we need n sub 2 minus x sub 2 to be at least 10. So if we go back up to our study, x sub 1 was 231, and that's definitely greater than or equal to 10. And here if we take 1,000 minus 231, we get 769. So that is also greater than or equal to 10. So the number of cheaters in the wife group was 176. That's definitely at least 10. And then the non-cheaters would have been 1,200 minus 176. And if we compute that, that gives us 1,024, and that is definitely at least 10. Okay, so again, in each group, the number of cheaters and the number of non-cheaters, and all four of those numbers all have to be at least 10. In this case, no population sizes were given, so again, we're just going to assume that cap n1 is greater than 20 times little n1, and that cap n2 is greater than or equal to 20 times little n sub 2. Alright, so if all those conditions check out, then we have the conditions to run a two-proportion z-test. Okay, so in the last unit we looked at the the previous chapter we looked at the one proportion z-test when we had one set of sample data, and now we've got two that we're comparing, so we're using the two-proportion z-test. Alright, so step 5 is the test statistic, and so for that we also look at just the statistics before we look at the standardized ones. And again, we can either use the calculator or StatCrunch to get those. So on the TI-84 we would go into the 2-prop z-test screen, so we'd hit stat and arrow over to test and scroll down to find 2-prop z-test, and we would enter all of our sample information. So 231 out of 1,000, 176 out of 1,200, and we would highlight we want to test that P1 is greater than P2, and then we would hit calculate. Alright, so on your output screen, the very first step up here, you should make sure that that first line matches your alternative hypothesis, which it does, P1 greater than P2. And then on that screen we have our z-score, so there's our test statistic, standardized score. And there's P, but it's really not P, it's really the p-value. And then we've got our p-hat1 and p-hat2, so our two separate groups, and we have our pooled p-hat as if we would have considered that to be all one group. And using StatCrunch, we would get those same values here as well. So no matter what technology you use, you get the following. So from the husband data, we would have had x1 out of n1, so that was 231 out of 1,000. So that gave us 0.231. The wife data, we had 176 out of 1,200, which gives us about 0.146667. And so the difference between those, if we compute the difference between those, we get about 0.084333. So that sample difference is actually displayed in the StatCrunch output. It's not displayed in your calculator output, though. All right, and then that pooled sample proportion is where we just throw everybody together in one group. So we had 1,000 men and 1,200 women. So that becomes our denominator. And we're going to put all the cheaters in the top here. So we had 231 husbands who cheated and an additional 176 wives who cheated, so that becomes our numerator. So we end up with 407 total cheaters out of a total group size of 2,200. And so this, if we compute, becomes 0.185. Okay, so that is right here on our output screen on the calculator is our 0.185. So if we were to set up this test statistic by hand, and again, we do not need to compute this because we're just going to cheat and write down what we got on the view screen. But your calculator would have taken the difference between these two sample proportions, and then it would have divided by this yucky product under the radical here in the denominator. So that pooled proportion was that 407 out of 2,200 times 1 minus that 407 out of 2,200. And then we have 1 over N1, so 1,000, plus 1 over 1,200. Okay, and all of that is under a radical in the denominator. So thank goodness we do not need to calculate that. We're going to come back up here either on the calculator or on StatCrunch here, and we would get that score of about 5.07. Alright, and on those output screens we can get our p-value. So on the TI-84 that was about 1.96 times 10 to the negative 7. And on StatCrunch it just says that the p-value is less than 0.001, which is good enough for us in this case because we're comparing it to an alpha value of 0.05. So, it is definitely under our 0.05. Alright, so as we are looking at displaying what all of those numbers mean, so again, if our null hypothesis is true, so again, in the center goes the claim, we would expect a difference here of 0. Z-score on center is 0. But our actual difference between the groups in the sample, that p-hat1 minus p-hat2 was this 0.084 if we round it off. Okay, and the z-score corresponding to that difference was 5.07. Okay, and then the p-value, this was a right-tail test, so the p-value is going to be the area in that right tail. So that p-value is definitely less than or equal to 0.05. So since our p-value is less than or equal to 0.05, because that was alpha for this problem, we reject the null hypothesis. Whoops, one too far. So if we go to state our conclusion in context, if we reject HO, that means there is significant evidence to conclude HA, but HA said that P1 was greater than P2. So we need to write what that means now in words for the problem. But if we just go back up, we already defined what P1 was and P2 was, so we're just going to stick those words in there. So there is significant evidence to conclude that the proportion of all husbands who cheat, okay, so there's our P1, okay, is more than, okay, so there's this symbol, and then now we need P2, which was the proportion of all wives who cheat. Okay, so if we read back through that just to make sure that that sentence makes sense, so we've got there is significant evidence to conclude that the proportion of all husbands who cheat is more than the proportion of all wives who cheat. So in the above hypothesis test, we concluded that the proportion of all husbands who cheat is more than the proportion of all wives. A next question someone might ask is how much more? And that can be answered with a confidence interval for the difference between the two population proportions. So this should say, next question.